Hi, welcome back to this week's lecture, and we are at module 20. So, I did suggest that you should review the material in modules 18 and 19 before you go to 20, because 20 gets a bit intensive. Unless you understand materials from 18 and 19 altogether, you will have a bit of a difficulty in understanding 20. So, some of the concepts that you need are the fact that the cross couple circuit gives you memory element, and there is S and R which can change independently in the basic SR latch. Then we slapped on gating to it, and we said only when the gate signal is on, the SR latch will behave like an SR latch. If the gate signal is off, it will keep the values as it is. This still did not prevent S and R being changed simultaneously. So, we introduced the notion of what is called a gated D latch. In the gated D latch, we prohibit S and R from taking the same values by connecting them to the same input line, one with the complemented version and another with the uncomplemented version. So, you have to understand all of that, and finally also said latches are what are called level sensitive circuits. The changes in the output, there may be changes in the input, and this will reflect as changes in the outputs as long as the gate is turned on, as long as the enable of the latch is turned on. So, we need to be able to control that. And that brings us to this module, which is on flip flops. So, the word flip flop itself, it's a funny word. So, flip flop also means slippers, for instance. So, in this case flip flop actually means your values can go from 0 to 1 and 1 to 0, right. So, that is why it is called a flip and a flop, right. So, it can flip or it can flop. The flip flop is essentially a memory element. Again, it is just a bistable multivibrator. The first thing we will start with is what is called a D flip flop. So, we saw that the D latch has a shortcoming. The input should not change while the gate signal is asserted. So, otherwise what can happen is there are multiple events which can change, and you may not have a reference point with respect to the clock for that. So, once the enable signal comes in, we do not want changes in D to go to Q. If we want anything like that, then if you want to prohibit changes in D to go to Q, then the latch is not enough. Instead, we will design a circuit which will ensure that Q will change only during the clock edges rather than during the clock levels. So, instead of a latch which is changing Q when as long as the latch is enabled, we will ensure that Q in a flip flop will change only when the clock comes in. So, at the time of the clock, if there is anything in D, we will capture that. Any further changes in D will not be captured till the next clock comes in. So, this is called a D flip flop. So, the symbol for a D flip flop is as follows. We will see how these circuits come about and so on in one step after the other. The first thing is the symbol for a flip flop is usually drawn as a rectangle like this, a D input, and there is Q and Q bar, and in the latch we actually had just a single line coming in and we called it CLK. Now, we also have a small triangle kind of thing here. So, forget the bubble for a while now. We also have a bubble kind of, so we also have a triangle kind of a thing that is indicating that it is a flip flop. So, this triangle here, not the bubble, the triangle here indicates that it is a flip flop. So, if you look at a rectangle with an input here, two outputs named Q and Q bar and a triangle like this, that is a flip flop. If it does not have a triangle, it is a latch usually, and this bubble is something extra. So, this bubble is equivalent to inversion. We will come to that in a little while. So, the first circuit that we are going to look at is called a master slave D flip flop. So, what is a D latch? A D latch has D as a data input. Q follows data input as long as enable is on, right. That is what a D latch was. A D flip flop is going to have two latches connected back to back. So, you have something called a master latch which is in red, and you have another latch called the slave latch which is in blue. These are your basic D latches. So, we take two of the D latches, put them back to back, and we take the external input D connected to the master's D input. We take the master's Q or the output of the master latch connect it as input to the slave latch, and the output of the slave latch goes to the external world. So, in fact, the slave has two outputs, Q and Q bar. You tap those two, you get Q and Q bar for the external world. The Q bar of the master latch is not connected to anything, and from the external world point of view, it takes an input CLK and D. So, there is D and there is CLK, and there are two outputs Q and Q bar. So, you have two outputs Q and Q bar. So, the most important thing that we have done is we have taken CLK, we have given to one of the enables, we have given it directly, we will call that CLK1. To the other latch, the enable is negation of the CLK. So, CLK2 is the negation of CLK and CLK1 is CLK directly. So, in some sense, when if this latch is enabled, this latch is disabled. If this latch is enabled, the slave latch is disabled. So, at any point of time, there is only one latch which is enabled, the other latch is disabled. So, the first thing I want you to see is this fact, that since G is the enable for this, when CLK is on, master will be enabled, slave will be disabled, and when CLK is 0, master will be disabled and slave will be enabled. So, when we say enable and disable, what we mean is if CLK is on, then any changes in D can go to Q. However, because CLK2 will be off, changes in Q will not be propagated to the slave's Q. Similarly, if CLK is 0, then any changes in D here will not reflect as changes in master's Q, but if there is anything in master's Q, it will go to slave's Q. So, this is what the whole circuit is doing. So, the best way to think about that is, think of it as a black box first, it is taking two inputs, it is giving two outputs, and there is some interesting internal connections of the latches that we have done. So, to get you the D flip flop. So, this is called a master slave D flip flop. Specifically, this circuit becomes what is called a edge triggered circuit. So, this circuit is not level triggered anymore. So, it is not that at a particular level of the clock D gets copied to Q. So, once you connect it like this, with respect to this CLK, this D cannot be asynchronously copied to Q, which means the change in D can reflect as change in Q only at very specific time intervals, not any time that D desires to. So, there is also this bubble here, we will come to that in a little while. So, let us see a quick timing diagram. What we are seeing is, you are seeing the same circuit here and the symbol for that circuit is here. So, I have also put the bubble here because the bubble is necessary, and let us see how the circuit will work. So, I am assuming that CLK is a periodic signal, right. So, that is coming at on and off at some regular intervals. So, let us assume that this is some timeline, this is some timeline and so on. So, between this line and this line, vertical line here, that is one time period, between this line and this line it is another time period and what not, right. So, CLK is something periodic and that is coming from the external world, and D is also an external input from the circuit's point of view. You look at this a black box, D is an external input, right. Let us assume that D is changing whenever it wants to, right. So, the change in D is not with respect to the clock signal, D is an external input, it is changing whenever it is changing, right. Now, let us see the effect of this, the changes in D, and see what happens and what gets registered in the Q. So, Q of the slave is going as Q of the circuit. We will observe what is happening to Q of the slave. So, let us start with this point. So, there is one edge coming here, right. When clock comes on, see at this point, if you look at here, the clock is on. So, there is positive level here, right. So, whenever CLK is 1, CLK1 is also 1. So, this is 1. So, all changes in D which is coming into the master will go as Q of the master, right. So even if I do not know what is happening before the clock, so this cross kind of, this hatching kind of thing that you see there is something that indicates I do not know what the value of D is, or I do not care about what the value of D is. Let us see from this point onwards what happens. The clock came on. Once the clock comes on, the CLK1 is the same as CLK itself. So this is the clock for the master and this is the data for the master. Now let us see how the Q of the master will change with respect to D of the master. So as long as clock is on, you will see a copy of D coming on to Q. So we do not know what is happening till this time point, and after that it is at 1. So you see a 1, then it goes to 0 for some time. So it goes to 0 and then comes back to 1. So that is what happens here, right. And between this and this, CLK1 is off, right. So because CLK1 is off, this change in D will not change the Q master. So if you see the clock CLK1 here of the master, this is off, which means the master latch is disabled. If the master latch is disabled, then change in D will not change the Q of the master, right. So Q of the master is remaining stable. Finally again this CLK comes on, which means CLK1 also comes on. So when CLK comes on, so at the positive level it starts with the 0, goes to 1, then stays 1 till the clock is on, right. So you will see that happening in Q also. It goes to 0 because when CLK1 came in, D master is 0, it starts with that, and then it goes to 1 at some point, stays at 1 till the clock goes off. So when CLK1 goes off, again there are changes here, it changes from 1 to 0 to 1. However, those changes are not seen in Q of the master. And finally, when this signal comes on, when the third clock tick comes on, at that point D master is already 1, it goes down to 0 once, that is captured in Q master, right. So if you notice, what has happened is we just traced what is the relationship between external clock, D master and Q master. So if you compare D master and Q master, you can see that not all the transitions in D master are transferred to Q master, right. So a subset of the transitions are actually left out. So for example, this 1 to 0 transition, this 1 to 0 transition does not appear in Q master. Similarly, this 1 to 0 and 0 to 1 transition does not appear in Q master. So some transitions are captured, some are not, but master is still a latch. So whenever CLK1 is on, if there are changes in D, that will be captured in Q master. So now let us look at the connection between Q master and D slave. So with respect to the slave, the clock signal is CLK2. So CLK2 is the complement of CLK. So you can see this waveform CLK here and the waveform CLK1 here, they are the complement of each other, right. So when CLK2 is on, when CLK is 0, CLK2 will be 1, when CLK is 1, CLK2 will be 0. So we have a complement of each other. Now Q master is the same as D slave, right. So this is the same as D slave. Let us see what happens to Q slave with respect to Q master. So now what is the, when is this latch going to be on? Whenever CLK2 is on, right. So let us go and look at when CLK2 is on. So CLK2 is on at this point of time. So it is on here. So whatever is in Q, you copy to D, right. So CLK2 is on here. So at this point Q master is 1. So we don't worry about what is happening here for now, because this is the first time when CLK2 is on, right. So we know all the data input as well as, so here the data is not known, clock 1 came on, so we do not care about this, and CLK2 is off, so we do not care about Q of the slave here. So once we come past this point, this Q master is 1, however CLK2 is 1. So, when CLK2 is 1, Q of the slave should copy D of the slave or the Q master. So, it is 1, and at this point CLK2 goes off. When it goes off, there seems to be a transition on Q master to 0 and then back to 1, but that is not even seen by the latch, the slave latch, because slave latch is disabled at this point. Then the slave latch gets enabled again here. So, when the slave latch gets enabled here, we see that Q was already 1, so it copies that. When the slave latch is disabled, whatever value was there in the slave before the clock went off, that is continued. So, it was at 1 just before the clock went off, clock CLK2 went off, so it will continue in that value. Finally, again at this point CLK2 comes back on, at this point Q master is 0, so you copy Q master to Q slave. So, now if you look at Q slave has far fewer transitions than D master. So, if you look at the output of this whole circuit, the Q versus D relationship, Q has far fewer transitions than D. This fewer transitions is not the goal here, however, there is something else that has happened interestingly. So, I am now going to make a claim and we will verify that with the picture. The claim I am going to make is that this circuit that I did here, this overall black box, which I am going to call the D flip flop, is going to sample D only at the negative edges of the clock, and it is going to keep the value everywhere else. So, let me restate it. So, my claim is that this circuit here, this black box here, which is called the D flip flop, is going to sample, or it is going to check what the value of D is on the negative edge of CLK signal. If on the negative edge of CLK, if D is 0, it will copy that, if D is 1, it will copy that, only during the negative edge of the clock. Once the negative edge happens of CLK signal, then CLK will remain at 0, CLK will come back to 1 and remain at 1 and then again go back to 0, right. That is the periodic nature of CLK. During all these periods, any change in D will not reflect as change in Q of the circuit. This is my claim. So, let us validate that. So, let us go and look at CLK as a signal. So, I am going to look at CLK, D master and Q slave, because that is the black box's inputs and outputs, right. So, when CLK is 1, the change in input will not go to Q slave. So, that is clear from the picture. When CLK goes off, whatever is the value of D. So, what is the value of D when the clock goes off? D master is at 1. I am going to sample it just at one period of time. I am going to take, so just that one nick of the time when the clock is going from 1 to 0, I am going to observe the value of D. I will retain that as the value. Till the next negative edge comes in, right. So, I sampled 1 here, right. If I sample D here, CLK is negative edge. If I sample D, it is 1. I am going to keep it till the next clock edge comes in, and during this time period, D actually went to 0, went back to 1 and so on. All of that I do not care. So, essentially what I have done is I have sampled D signal only at this time point, and it is retaining it till the next clock edge comes in. So, when the next falling edge of clock comes in, at this point again D is 1, right. So, if you observe at this point, it is again at 1, and I will keep that as the value and continue that, keeping that value at Q till the next clock edge which is falling, which comes through. When that happens, D is 0, and when D is 0, Q of the slave, right, is 0. You can see that Q slave or Q of the D flip flop is actually following D master or D of the flip flop, only that it is not following the signal waveform blindly, it is sampling D master at whenever there is a negative edge. So, this clock in some sense is our triggering signal, and at this triggering signal we are going to come and capture the values. So, the analogy that I can give is, let us say I want to take attendance in a class and I have a camera which is set up in the class, and I have some algorithm which will figure out the faces and figure out who is in the class and who is not. Let us say I have all of that. What I am going to do is, at 8:50 I will take a picture of the class, right. Whoever is in the class at that point of time, they get attendance, right. So I sample it, and whoever is at whoever is there in the class at 9:50, they get attendance. So it is possible that people walked in at different points of time starting at 9 o'clock till whatever time it is, but at 9:50 if they are there in the class, I am going to treat that they were in the whole class and I will give them attendance. Let us say I do that, then all I am doing is I am not continuously monitoring who is in the class from 9 o'clock to 9:50, I am just going to take a snapshot of it at 9:50, I will treat that as my data. That is the same thing that is happening here. On the negative edge of the clock, whatever is in D, I am going to copy that, and in all the rest of the time till the next negative edge comes in, I am not going to care about D. So let us look at the characteristic table. So this is a CLK signal, we are showing it as a downward going arrow. So that means it is a negative edge. So on the negative edge of CLK, if D is 0, Q should be 0 and Q bar should be 1. On the negative edge of the CLK, if D is 1, Q star is 1 and Q star bar is 0. In all the other cases, Q star should just keep the value of previous value itself. So Q of t should be the same as Q of t minus 1. So this is called a negative edge triggered flip flop. So the reason it is called negative edge trigger is that the sampling of D is done at the negative edge of the clock. If I do sampling at the positive edge of the clock, that would be called a positive edge triggered flip flop. So now let us go back to this picture here that I showed, right. So in this picture what we have is, I put a bubble here, right. So a positive edge triggered flip flop which samples the value of D only when the clock edge rises, that is called a positive edge triggered flip flop, that will not have this bubble. When you see a bubble, it means that it is a negative edge triggered flip flop. So if you see a rectangle with 3 pins for D, Q and Q bar and just a triangle like thing, that is a positive edge triggered flip flop. In this flip flop, in the positive edge triggered flip flop, D is being sampled only when the clock rises. In the negative edge triggered flip flop, D is sampled when the CLK signal falls. So once you do this CLK1, CLK2 and so on does not matter. You can now think about this whole circuit, this D flip flop as a black box. What does the black box give you? Whenever CLK comes from 1 to 0, D will be sampled, in all the other time periods Q will be retained. That is the characteristic table of a flip flop, D flip flop which is negative edge triggered, and it is still following D. So that is why we call it a D flip flop or the data flip flop. It is still following D as it is. There is no special meaning attached to D here. D is not set or reset or anything, right. Whatever the value of D is, we are passing that on to Q. So it is just the data input, only that we can now forget the fact that it is actually made of 2 flip flops and there is some careful connection inside and so on. We can now go up in one level of abstraction and we can start using this circuit as a D flip flop as it is. So I will treat it as a black box, I will not show the connections later on, right. If I only when I need it I will show it, till then I will assume that a D flip flop is just this external black box. I will assume that you understand what the internal details are, alright. So now we have something called a D flip flop. There are lots of interesting things that you can do with the D flip flop. So I want to show a quick summary of what this level versus edge triggering means. So in this circuit I have 3 different logic elements, sequential elements. On the left side you have a latch. So a latch is just D, Q and Q bar and an enable signal that comes in. In the middle is the red one which is actually a positive edge triggered D flip flop. So this flip flop will capture D whenever the clock signal goes from 0 to 1, otherwise it will ignore the changes in D, it will keep the values of Q. And this brown one is the negative edge triggered D flip flop. So you have 3 logical elements, all are memory elements. This is a latch, this is a positive edge triggered flip flop, this is a negative edge triggered flip flop. What if we give the same D and clock to all of them, what will be the behavior on QA, QB and QC. So, this is not a circuit that is useful for any practical purpose, this is just to show you how these circuits behave. So, let us assume that clock and D are as follows. So, there is clock and you have this here, and D changes several times, no matter where clock is, D is changing asynchronously with respect to CLK. What I mean by that is, the changes in D are not aligned to changes in CLK, right. So, it is changing independently of CLK. So, D is asynchronous with respect to CLK. I now want to synchronize D with respect to CLK. Now, let us see what happens for the blue latch first. So, QA is the output of the blue latch and it is a positive level triggered latch, which means when CLK is 1, D will be copied to QA, and when CLK is 0, whatever the value of QA is, it will continue. So, let us see this part first. So, during this part CLK is 1, whatever you see as change in green till here is appearing in the blue waveform, but once the clock goes off, there are changes in the green waveform here which are not reflected here. It is just, so at this point QA is 0, it is just continuing here, right. And again when the clock comes on here, QA should start following D. So, in this part is actually QA following D, but QA is also 0 earlier, so you do not see any transition here, but the transitions to 1 and back to 0 and 1 are captured, and this transition from 1 to 0 is not captured because at that point CLK is off. So, the A latch is disabled. So, this is what happens for the latch. Let us look at the positive edge triggered flip flop. So, remember there are two latches inside, the master and the slave latch. So, in the master and the slave latch, so if I go and use this abstract thing, whenever there is a positive edge I will sample D and I will keep it till the next rising edge comes. So, there is a rising edge here, when this edge is rising D is already 1, so I am sampling 1, I will keep it till the next clock's rising edge comes in. When that comes in, D is 0, so I am going to keep that 0. So, this is what happens for QB. QC is actually the output of a negative edge triggered flip flop. What this is going to do is, it is going to look at what are the values of whatever is D when it is falling, when the clock is falling. So, when the clock is falling, the output is, the D input is 0, so it keeps 0. The next clock signal falling is here, at that point this is 1, so it rises to 1. So, QB and QC are themselves different, and QA is of course different from QB. In fact, QA and the master latch of both these two, I am sorry, so the QA and the master latch of this red flip flop will have the same waveforms. However, QB is tapped from the slave latch of the D flip flop, so that is having a different waveform, and there is no direct relationship between the waveform QA and QC. Even internal signals of this flip flop will not match the signal of QA. So, that is the overall setup now. Hopefully, this picture explains to you what the difference between latches and flip flops are. Right. So, now let us move on. So, I am going to show you two different kinds of circuits. So, one of the circuits is what is called a flip flop with a preset and clear. So, if you notice, this part is the slave latch and this part is the master latch, right. So, forget the blue lines and the green lines now. So, this is a cross coupled SR latch and you put two gates before that and a common signal that is driving both, right. So, that would mean it is a gated SR latch. So, this part is a gated SR latch, this part is also a gated SR latch, and before the gated SR latch there is a common D that is coming to both. So, this part is a D latch. So, you have a D latch followed by a gated SR latch here, alright. On top of that, what we have done is we have taken a signal called preset and we have given it to these two gates here, we have taken another signal called clear and we have given it to these two gates here. So, the rest of it will resemble the circuit, internal circuit for a D flip flop actually. If you go and look at it, if I remove the blue lines and if I make this all these 3 input gates as 2 input gates, that is actually the internal circuit for a D flip flop implemented with NAND gates. On this flip flop, we made these 4 gates as 3 input NAND gates and we are bringing a signal called preset here and bringing a signal called clear here. So, in fact, this is a negative edge triggered D flip flop. Okay. So, now let us see what the preset and clear does. So, the first thing to notice is preset is not just preset, it is marked with preset underscore n. So, what we are doing here is what is called negative logic. Right. So, first of all the word preset means, so you want the flip flop to be 1 even without data input. So, if the data input so this is not P reset, it is preset. So, whenever preset is on, so this is something that you do when the circuit actually comes up, you may not have any data input, you want the flip flop to have 1 at the output, there is no data input so far. So, in those cases you want to bring a preset. So, a preset of 1 means the flip flop should be set to 1. When you say preset underscore n, what we mean by that is, if this line preset n is 0, then Q should be 1. If preset n is 1, then the circuit should work as it is. Similarly for clear, if clear is 1, Q should go to 0. If clear is 0, then the circuit would work as it is. That is the usual meaning of preset and clear. Preset means set the value of the flip flop to 1 and clear means set the value of the flip flop to 0. Only that when you put a negative underscore n, it means we are using preset bar and clear bar. So, when preset bar is 0, it means preset is 1, we want the circuit to be preset. So, let us put a value 0 in the signal here. If I put 0 in this wire here, this 0 will go to this 3 input NAND gate, you will see a 1 here and the same input goes here, Q will also become 1. So, without actually looking at D or clock or anything, we are able to change Q to 1 by just bringing this preset n line to 0 or preset bar to 0. So, if preset bar is 0, preset is 1, we want the circuit to be preset. Similarly, I can bring this clear n, if I bring it to 0, no matter what D and clock are, this line will become a 1. So, if I bring this as a 0, this will be a 1 because of this NAND gate and this will be a 1 because of this NAND gate. And if Q bar is 1, Q will eventually go to 0. Right. So, Q becomes 0 when clear becomes 1. So, if preset is 1, Q becomes 1, if clear is 1, clear n is 0, then Q becomes 0. So, this is the meaning of preset and clear. The only thing is both the preset and clear signals can actually be brought in without any reference to the clock itself. So, therefore, preset and clear in this circuit are actually asynchronous inputs. They can change no matter whenever they want to, they do not actually have to align themselves with respect to the clock input. Right. However, D actually aligns itself with the clock input. So, if both preset and clear are off, the rest of the circuit is a D flip flop and change in D will not go to Q unless the clock signal samples it at the negative edge. So, this is called a asynchronously resettable and presetable D flip flop. So, the symbol for that is as follows. Typically, you put 2 different lines here and these bubbles are actually meaning that they are negative logic. So, if you do not have the bubbles, then if preset is 1, Q will become 1, if clear is 1, Q will become 0. So, clearly you do not want preset and clear both to be 1 at the same time, right, then there is no meaning attached to it. So, we will ensure somehow in the circuits that are driving preset and clear, you do not drive both of them simultaneously in general. Then you have the clock input here, which also seems to be a negative edge triggered flip flop. So, this flip flop is a negative edge triggered D flip flop, which has asynchronous negative preset and asynchronous negative clear. So, this is the meaning of the logic block. You can make the D flip flop with synchronous clear, you take the D input and put clear bar as another input to an AND gate, you give that to a regular D flip flop, right. So when you do that, if clear bar is 0, right, which means clear is 1, so we want the Q to be cleared. If clear bar or clear N is 0, then this D input will be a 0, so if the clock samples it correct, then Q will become 0. It doesn't, it completely masks the D value. However, if clear bar is, so if this is 1 or clear is 0 means you do not want to clear the flip flop. If clear bar is 1, D will come as input here and that is passed down to Q provided the flip flop catches it. So what we have is a D flip flop with a synchronous clear. So change in clear will not change Q unless there is a clock edge that comes and samples clear also. So D is a sampled signal always for a flip flop, clear is also sampled in this example, whereas in the previous example clear was not sampled. Then let us look at a circuit called a T flip flop. T flip flop is an interesting circuit. So T flip flop is actually a minor variation of the D flip flop. So let us look at the circuit. You have a D flip flop and there is some circuitry here. This circuitry is actually doing the function of a mux or a multiplexer. So if you describe the output of this OR gate in terms of the inputs, namely T, Q and Q bar, we can see that this OR gate is doing T bar and Q or T and Q bar, right. So that is the definition of a mux, where Q and Q bar are the input lines and T is the select line, right. So if T is the select line, this circuit is actually a mux. So this circuit is either choosing Q or Q bar depending on what T is. So if T is 1, then it's the flip flop will toggle its current state. So let me restate this. If T is on, then this circuit will toggle its output. If T is off, it will keep the previous value that it contained. So a T flip flop or a toggle flip flop changes state on every clock if the toggling is enabled or if T is 1. So let us put T equal to 1 for a while now. If T is 1, this is 0, which means this line will be a 0. If T is 1, 1 and Q bar will come here. So you have 0 or Q bar, 0 or Q bar is Q bar, Q bar goes as D input. So when the clock comes in, let us say it's so this is a positive edge triggered D flip flop, right. So when the clock comes in, Q bar will be copied to Q. So if Q was 1, Q bar would have been 0, so it will become 0 now. If Q was 0, Q bar would have been 1, it will become 1 now. So either way Q toggles. However, if T is 0, then this is 1, so you have 1 and Q that goes as Q, and you have 0 and Q bar that goes as 0. So you have Q or 0, that is Q. So the D input is Q, which is the previous state of the flip flop itself. So the previous value was also Q, right. So when the flip flop's rising edge clock comes in, it takes the same value and copies it back to Q. So in that case, when T is 1, right, the circuit toggles the value. If T is 0, the circuit does not toggle. So the characteristic table and the picture are shown below. So if you mark the inside pin with T, it usually means it is a T flip flop. If you put a D, it is a D flip flop. If you put T, it is a T flip flop. As before, we have the small rectangle, a small triangle here to say that the signal that is coming in is a first of all for a flip flop. So this block is a flip flop, and the absence of bubble here says it is a positive edge triggered T flip flop, and you have two outputs Q and Q bar. The characteristic table is given here. When T is 0, Q of T plus 1 is the same as Q of T. When T is 1, Q of T plus 1 is Q bar of T. Right. This is a toggle flip flop. This toggle flip flop is quite handy if you want to toggle some signal in every step. So this is a very nice and handy circuit to have, and This brings us to the end of module 20. So, what we have seen so far is in this module, it is a heavy duty module. We saw the basics of a D latch in the previous module. We started from there, connected them back to back, and we got what is called a D flip flop, and the D flip flop is a master and slave combination. So, the master samples when the clock is on and the slave samples when the clock is off for a negative edge triggered D flip flop, and the combination of that seems to give us this thing. In some sense, there is an intersection between these two sampling points, and that sampling point is the negative edge itself. So, in summary, D flip flop will sample the D input whenever the clock goes from 1 to 0, and in the rest of the time it will keep it as it is. So, this is the definition of a negative edge triggered D flip flop, which we saw in the class. If you want to get a positive edge triggered D flip flop, all you have to do is the CLK signal going into CLK1 and CLK2, change the inverter, put the inverter on CLK1 line and keep the CLK2 line as it is. That will be a positive edge triggered D flip flop. We also saw how this D flip flop with additional circuitry can become what is called a T flip flop. So, I suggest that again you go back and review the video once more if something is not clear, and also go and check whether the waveforms that are all drawn, whether you are able to understand it and reproduce it. So, the circuit that I gave, right, with QA, QB and QC, see if you can actually draw your own waveform for D and see whether QA, QB and QC are with respect to the understanding that you have for each of those circuits. So, that brings us to the end of module 20. I will see you at module 21. Thank you very much.